Tell me if you don't hear me, okay? I'm French guy, so I speak with a very bad accent, so sometimes it might be complicated, especially for English people. Anyway, so let's start. So today we are going to speak about this, but actually it's not exactly this, because I've changed completely the way I wanted to do the talk last week, because the talk has been designed this week, because at the beginning it should have been just a live coding session for type level conference, and conference actually, and it has transformed into a talk. So this is not exactly that, but it's a bit that. So I'm Pascal Voitot, I'm a French guy, I live near Paris, and I work for an American company called Project September, this one. And we develop an application for social commerce in the domain of fashion and style. So what's interesting is not the subject here, even if the application is quite cool. It's more that the backend is developed fully in Scala from scratch. So we had no code at the beginning, and we started from Scala, and we have developed everything trying to follow as much as possible functional programming principles and also lots of type level programming. So why have we done that? It's because we know it works. We wanted also to have some code which is very robust, and we wanted to trust a lot in our code. We are a very small team for the backend. We are only 3, and we don't need many more people actually. And that's also the power of a language like Scala, that you can develop big products with a few people. So my own experience, so I've done lots of C in the past, and a bit of C++, which was the most horrible language in the world, but quite funny to learn. And then I had to switch to Java, and especially Java Enterprise stuff. So I spent some years, a few years in this domain, and I must say, it was quite painful. And I ended like this, exactly, you know. And I must say, after these years, I wanted to do something else, okay? Maybe, I don't know, farm some goats and do some cheese, I don't know, something else, because it was unbearable. But I decided to try other languages. So I decided to learn functional programming languages, and the one which was the easiest for me was Scala, because I was used to develop using JVM, and it was quite easy to sell Scala to my boss. So I decided to learn Scala, and that's my state right now, okay? Okay, so Scala is quite cool for that. Anyway, let's start with the serious stuff. So here is a painting from René Magritte. Maybe, who knows René Magritte here? Okay, nice. So this guy painted this in 1929. And here you see something that has all the attributes of a pipe, right? And just under it, there is a sentence, ceci n'est pas une pipe, which means this is not a pipe, okay? So you see something which looks like a pipe, and this is written, this is not a pipe. So maybe you can wonder what René Magritte wanted to express in this stuff. So he was a surrealist painter, right? And surrealism is very interesting because it's speaking about things you feel, about the functioning of thought, about everything which is abstract, okay? And sometimes the interpretation can be very, fuzzy. It's not clear, okay? And you can interpret it in the way you want. So, but here, what did he want to say? So you can have some pretty deep philosophical interpretations, or very simple one. For example, he said, René Magritte, about this painting, if I hadn't written ceci n'est pas une pipe, I would have lied. Okay? So what does it mean? It's just that the image of a thing is not the thing itself. Okay? It's just a representation, right? So if we apply the same principle to our job every day. No, sorry, I skipped a slide. So let's analyze a bit what Magritte did in the process of thought when he created this painting. So the painting is called The Treachery of Image. So he wanted to express the idea of the treachery of image. So what did he do? He made a first representation, his own representation, about the concept of the treachery of image. So this is an internal one. It's his own words, his own creation, his own vision of the treachery of image. Then he has decided from this description to go to the description of the pipe with this sentence, which is contradicting what you see, okay? And finally, he has decided to do a third representation, which is to share it into a common language, which is a painting. So what has he done? He has done a representation of a representation of a representation, right? So now let's go to what I was saying. So if we do an analogy with our application that we develop every day in our job of developers. So we do a first representation of our business model. It's a description. We integrate it in our own model of thinking, and it's not a vision which is objective. It's completely subjective. It's your vision of the business domain with the functioning of your own thought, right? And these are your own words, your own rules, and this is purely your creation. So you have full control of this part because it's your internal representation. The second thing you are going to do is to do a translation of this description or specification into some code. And the code is made to be shared to others because you never work alone, okay? You need to share it to other people, you need to work together, and you need to say exactly what it's going to do. And when you share it publicly, it's called open source. And we all know it's very good, okay? So here you do a second representation, and you are going to write your logic into a programming language. And finally, you do a third representation from this language of programming into the world of machines. So it's compiling, for example, for Scala or for Haskell. So you're translating your logic into the execution domain and the resource management. This part is quite boring because you have no control on that because machines are outside of your world and you don't know exactly how it works and it's boring. You have to say if it's going to be parallel, sequential, if it's going to be synchronism, asynchronism, and whatever. And you have to deal with something which is about hardware, and it's no more it's no more about yourself. It's external to you. So you can do everything you want, you don't control it completely. So this is running the application naturally. So what have we done? We have done a representation of a representation of a representation, right? I told that René Magritte told about the treachery of image that if he hadn't written this sentence, he would have lied. So representation can lie, actually. And this is another painting of René Magritte called Golconda, and he's expressing that in it, so I'm not going to speak about it more. But when you can lie in your representation, it also means it's your own responsibility. You need to be responsible in what you put in your translations, in your interpretations. And the result is not something which is independent of you. It's completely what you want to say. So interpretation can lie, or sometimes not. So we are going to apply a bit the same logic to other representations. We are going to take the same principle as treachery of image and apply it to other representations. So here is an image. So you have here, this is not the president of the USA, and you see a guy. Is it a lie or not a lie? Nobody knows? So this guy actually is Obama when he was younger, okay? So it's not exactly a lie, okay? So I take another one. This one. This is James Bond. So is this James Bond? So what you see here is a guy. He looks like Sean Connery, a bit hairy, with a gun and some red pants. Weird with red pants, actually. Is this a lie? Is this James Bond? What do you believe? No. Who is it? You don't know? Actually, it's not a lie, and it's not a lie, actually. It's more than that. This guy is Zardoz. You know Zardoz? No, maybe you're too young. You have to watch this movie. It's a movie from the 70s, which is crazy. And the slogan of the movie is Beyond 1984, Beyond 2001, Beyond Love and Death. And it's really surrealist, okay? You can watch it. It's cool. Anyway, let's go back to serious stuff. Okay. So we have two levels of representation, which are, you build a description of your business logic, and then you are going to translate it into execution and resources. This part is about you. It's about human world. And this part is about machine world. You haven't fully control on this part, and you have full control on this part. So the problem globally is that we use one single host language for all our description. We describe our business logic in the same language as execution and resources. And the problem is that, so due to history, all our machine-oriented languages, except a few ones, are based on the machine world. They represent how machine works. So if you take C, for example, it's exactly the translation of what the machine is into a language. And then we have built on this machine, on this language. So it's good. These languages are good at expressing execution and resources, but not very good at expressing human things. So what we would like, ideally, is to separate those. So we want to be able to describe in our own language, which is DSL. So Aaron has been speaking about DSL this morning, so domain-specific languages. So this is your description, this is your words. But you want to write it in the host language because you don't want to manipulate many languages at the same time. And you want to be able to manipulate execution and resources with the same language and some helpers to make it better. But you don't want to have the same stuff exactly. You want to be able to separate both. There is something else you want to do, and all Java people know about it because when they use Spring or whatever dependency injection stuff. So you want to have one single description and to be able to execute in different domains. So for example, you want to do some functional tests with some dummy data, and you want to execute it with one type of database, another type of database. You want to be able to deploy it on one machine, on a cloud, on whatever you can imagine, change the network, etc. So you want one description and several execution domains. And also, this part, as I said, is boring. You don't control it, so you want to push it further from you and to focus on the description, which is more interesting and which you control a lot. So, what do we do? How do we go there, actually? The question was, how can we help reach this state of separation? So what we have done is to instrument our languages with some tools. So I'm not going to spend a long time on this part because I'm not interested in it today. So for execution, we have some principles like immutability, referential transparency, even monads, to help us manipulate our resources in a more robust and sure way. On the other side, for the description, this is a problem because our languages are not made for that. So what we have done is to bring external tools, like the types, to represent our business constraint, and also to prove what we are doing. So when you use types in your coding, it's not only to have some simple constraints, you can also really translate your business constraint and prove that what you are doing is exactly what you pretend to do. It's very important. You have also the behaviors on all the laws you want to respect in your code, which can be encoded with type classes. You need sometimes also to extract some generic mechanism in your code, and you want to be able to replicate the same mechanism, which is generic, in different cases. So for that, you're going to use some higher kind, for example. And also the monads, which are very useful to represent a flow of a sequential flow of operations, which corresponds quite well to our logic of thinking. So globally, when you see that, all of these tools which have been added to our languages to help us manipulate execution and description at the same time are all based on one single foundation, which is mathematics and logic. Okay? Mathematics is not here just because it's fun and because it helps people to think different. It's also because it's really useful. And every day, so all the languages are based on mathematics, but all the tools we use here to make it better are also based on mathematics. And mathematics allow to express better our thought, but also the functioning of our thought in what we do every day. If we go back to the definition of surrealism by André Breton, so this one is the original one, so it's about expressing the real functional of thought. So that's what I was saying. And there is another one, another sentence. Dictation of thought in the absence of all control, exercised by reason outside of all aesthetic and moral preoccupation. What is the activity, the human activity, which fits the best to this definition? It's mathematics. Mathematics is exactly about surrealism, okay? It is it, actually. And that's a very interesting idea, because expressing the functioning of your thought is very important. You are always representing stuff. You can lie. You are responsible. And when you do mathematics, that's what you do. And that's the most human activity. So that was the most important part of my talk. The rest is boring. It's about code. Okay? So if you want to sleep, it's now. So we are going to apply this principle for real in real application. So we want to describe and then to execute a bit further, and we want to separate it as much as possible. We are going to do that in Scala. So Scala, you can criticize it, you can think it's not functional. It's a pretty good functional language. The type level programming in Scala is pretty good. It has defaults. It has also cases where when you want to destroy Scala, but globally you can do pretty good things, and it runs very well in production. And you can sell it also right now, so not tomorrow, right now. You can do good, big project in Scala, and it works. It's not only, so you can do also in Haskell, but it's a bit harder to sell to companies. So, first of all, the specification, the description. So we are going to, so now there is a big issue in the world, which is not so fun, about immigrants. So we are going to develop an automatic border checking system. So the specification is papers, please. And papers, please, I don't know, who knows papers, please? Okay, so for the other ones, it's a small indie game, which is very interesting. So you're a border officer and working in a kind of dystopian dictature, and you have to let people pass. So you have to check passport, image, and photo, and other details, and check it and let them pass or not. And when you don't let them pass, they will beg you because please let me pass, because if you don't let me pass, my family will be killed, and it's horrible. Okay, but if you let them pass, in this case, what happens is that you endanger yourself, and you can be put in jail, or your family can be killed also. So it's pretty interesting because it's mixing kind of humanity and obeying. So we are going to develop this, but a bit simpler, okay? So first of all, I want to express my logic very simply. So I don't think at all how it's going to be executed. I don't care. I just speak my words and my logic. So for example, so I receive a person, so I pass it to my logic, and then I'm going to ask the passport, to take a photo, to ask the fingerprints, then I check it with an ID service. So it's just something which will tell me if it's okay or KO. And then I'm going to log it, if it's okay, and let it pass. If it's an error, I say, no, it's not good. And then I'm going to call this weird logic does dystopian, which is just something representing the logic of the game. So I'm not going to expand this part because it's too long. And then I call the police, and they are going to eject the poor person, right? So this is my logic. I just wrote my own words using some Scala syntax, but actually it could be written in any language in the same way. Remark that I use a for comprehension because it's a monadic flow, because monadic flows are very good at representing sequential operations. So I'm doing something which is sequential, and it's good. So I'm going to use that, and I want to use that in Scala directly. So what we have here is the DSL. So person DSL has two verbs. So you have ask passport or ask fingerprint. And you have a return type, which is a picture, a passport, a fingerprint, and a status. So I'm just going to encode now my grammar in Scala. So it's very simple, actually. So I create my case classes. So here, imagine you would have some members, okay? And then I just create some sealed threads with a payload. So it's not a simple type, it's a type with a payload, because I want to return something, which is a picture, a passport, or a fingerprint. And then I'm just implementing the verbs, which extend my DSL. So that's exactly what Aaron was presenting this morning. It's just my grammar, nothing interesting here. So if I compile this part, the logic I showed you earlier, it will tell me that value flat map is not a member of person service.shoot. Yes, it's just, you see, it's nothing. This part is just a structure, okay? There is no flat map. It's not a, so you know that to have a flat map, you need to prove that it's a monad. But this stuff is not a monad at all, so it can't work. So our f of a are not monads, right? So the question we have is, can we make them monads? So who knows the answer? I know some people will know it, yes. So what is the answer? Yes, why? So yes, no, not only free, also coioneda. So I'm not going to talk at all what is a free monad or coioneda today. You have lots of talks about it. It's about mathematics, and it's not very interesting actually. We are just going to use them. Why? Because actually what we want is just a mathematical construction which is completely artificial, and we just want to delay the need of monads. Because what I was describing here is just a monadic flow. So it means sometime I will need a monad, right? So I'm just going to focus on delaying the need of monad, and for that I'm going to use a coioneda, which is also called a free functor. So I'm going to take my f of a, transform it into a functor using a coioneda, and then I'm going to transform it into a monad using a free monad. But that's all, it's artificial. So what I want to do is just to transform all the lines to free monads with coioneda also. So I lift every line with lift free C. So it's a fake code that doesn't exist, okay? So the problem we have now is that we have lots of free here, it's cool. So these are monads, so we have a flat map with a free monad, so it should compile, but it won't compile actually, because all the lines have different types. So here you have a picture service, a person service, an ID service, a log, and a police service. So this will not compile in Scala because, as you know, in a for comprehension, all the lines must be of the same type. So that's another problem, right? So types are not the same. So what can we do? So the free part is not going to change. The result, we don't care about it because it's just passed along the monadic flow, and the rest, we can do something with that. So here, when I say it, I have a picture service or a person service or an ID service or log. What is that in mathematics? Yes, it's a sum, a coproduct. So we are just going to sum our f of a in something like this. So we have a type, PRG, which is a log or picture service or person or police or ID or logic. Right, that's what we want. The problem is that it doesn't exist in Scala. So we have in Scala, in cat, there is a coproduct. So where is Raoul? Is it you? Raoul?
I ported that from Scala.
Yes. So there is a coproduct which is just for two elements. So if you want to do coproducts with this kind of stuff, you need to do coproducts of coproduct of coproduct. It's a bit boring to use. In shapeless, there is a nice coproduct, but it's not made to manipulate f of a. It's aimed to manipulate f, okay? And it's not good for this stuff. So that's where we are going to talk about Freek. So Freek, what is it? It's that, just that. So I'm going to provide an operator, this one, to do the coproduct. So it's type PRG equals log or picture service, etc. And an ending one, which is just to end the coproduct because it's in Scala and we have to do that. You have the same in shapeless. And you have this one, which is a val, which is a bit cut, PRG equal DSL.map of PRG. So this one shouldn't exist, okay? But we have to, I have to do it for now in Scala because it's purely artificial. The aim is to let Scala build the type, the coproduct type as I want immediately and to be able to use it later, especially when the logic is recursive. So I have to convince Scala here, Scala C, and okay, that's my hate and love relation with Scala. Okay, sometimes the language is very annoying because you have to, you hit limits of the compiler and you shouldn't. It's exactly the same as SI 2712 that Miles was describing today. But what is very cool with Scala C is that you can convince the compiler that it should work. You know, it's a bit like, hey man, hey guy, you can do it, okay? So I'm going to push you a bit, so you can find some workaround with some implicit, some kind of weird stuff, and then you're going to write horrible code, but at the end, the compiler can be convinced he knows how to do it. And that's a bit crazy, but it works, and that's how we make Scala progress right now. And sometimes we find also a way to solve it in the compiler, like SI 2712 patch. And that's far better naturally, but yes, we have to start by convincing the compiler. Anyway, so Freek, what we want to do now is to lift all the lines to the same type, which is a free of the coproduct of all our DSL. So you just write this, so for every line, so it's a bit painful, right? But you have to write .freek of PRG, and that's finished, okay? This part here, so I commented it because you don't need it. You let Scala C infer it, but I wrote it because you can write it and it will give you exactly that. And you see here the PRG. So my aim with the val PRG is just to infer the coproduct here. And it's very useful when I have a recursion in the program, because you need to provide the type of the function in a recursion. So that's Freek, and it's finished, it works. It's a bit magic, but actually it's not magic at all. So to tell you the history of Freek, so we work at Project September, and we have started using some cake patterns, but not exactly a cake pattern, a kind of hybrid cake pattern, because cake pattern, I don't know if people know about it. When you have a big cake pattern, you hit some limits, like so you have the time of compiling, which can become crazy, and you have also some problems of initialization order. And as soon as the cake pattern is big, you don't control at all how it is going to initialize, and sometimes you have some null pointer exception at runtime, which is quite annoying for Scala. So we wanted to try some alternatives, and I have a colleague, he doesn't know at all about free monads and all of this stuff about Coyoneda. But he was catching the principle that he could describe and then compile it into an execution. And he wanted to try that, and I saw that, and I said, oh, you're going to eat problems with type. And I decided to write this library just to help him and to remove the type boilerplate. And actually it works quite well. And it's quite cool. So there is only one thing we needed, which was the SI 2712 patch, because we are manipulating f of a. And the problem that SI 2712 has is exactly what we encounter in this case. So that's why I've done all of this. And it's nothing that we use the normal free of cats. There is nothing around it. We have some helpers to combine DSL. The only specific stuff I've been developing is this higher kind coproduct, because shapeless coproduct was not enough. So it's about 500 lines of code, and the rest is about 300 lines of code. If you look at the code of this, yes, it's pretty ugly, because, yes, that's the syntax of Scala. But it's just to prove all the cases I need, and if you know, I should write a comment before every implicit, and it's quite clear, actually. But it's painful to write. So that's Freek. So now we have the boring part, which is the execution. So we have a free DSL, okay, which represents exactly what we wanted to say, and now we are going to execute it. So I take my DSL, and I'm going to compile it into a monadic domain of execution. So we were talking about monads. The logic was a for comprehension, so it's a monad. But the idea in all our languages, like Haskell or Scala, is to abstract the domain of execution, and the best way we have for now is monads. So in Haskell you have IO monads, and in Scala you have different kinds. You have FS2, Monix, Scala Z task, and you have also future in the Scala core, which can be criticized a lot, but which works also. So the idea is to go from this DSL into this monadic, and then we are going to compile it with Scala C into the language, the machine language. And for that, we use a natural transformation. So Aaron presented them this morning, so I'm not going to spend much time on it. So it's just a transformation from this DSL of A into M of A for any A. So here I'm translating into a monad, but actually you have to know that the translation here could be something else. It doesn't need to be a monad. I can translate my free into something else, even into another free, okay? It's just interpreting into another representation. And you choose the representation. And as I said, the representation is never objective. So here is the Scala code I write. So I write an interpreter, which is a natural transformation from DSL to M. I write my program, which is a value here, okay? And you see the free, it's exactly what I said. I can use this value many times. it's immutable. The program is written once, it's a data structure, and I can reuse it many times, interpret it many times. And then to run it, I'm just going to fold map. So now it's called compile in latest version of CATS with this interpreter. And I have a M of A here. So I'm not going to spend a long time on that. So it's about multiple domain of execution. So I'm writing my interpreter. So here is how you write in Scala a natural transformation. So you have from log to task. So I'm just using for all the verbs of my DSL, I'm going to write what it does. So here I'm translating the DSL, which is something very abstract, into something doing something for real in my language. And for here, it's exactly the same for the picture service. So I'm going to picture service to task, and here I'm going to use a real camera. Okay, so I'm injecting actually here. So you can say I'm pushing the problem a bit further, and it's not false. Okay, but it's better because you have really isolated this part, and in general here it's just a class, and you don't need to have complex patterns, cake patterns. And if you want to do something simpler, you can just interpret it into an ID. So this would be, for example, a dummy picture, a mock, and here it's just for testing. So I can have one description, several execution domains. So the problem actually is because now, so we have one DSL, but we haven't one DSL, we have a coproduct of DSL. So what do? We just have the type, which is the coproduct, and we are going to provide one interpreter for every DSL, okay? And we are going to use, to squash this into one single interpreter. So here you have the coproduct, I provide a product of the interpreters, and I squash it into the transformation from the coproduct into the monad. And then I pass it to the interpreter, and at the end I will have a M of A, and it's finished. Here is how you write it, one interpreter per line. I just use this operator, which is an AND, no more an OR, because it's a product. And at the end, I will have a prg.cop to task, natural transformation. And this is what Freek provides. So we provide also the combining of DSL, of interpreters. And finally, we execute it. So I use papers.please.logic of my person that I've received, and then I interpret it, and I've got a task of result at the end, and the rest is not interesting, as I said. Naturally, Freek is based on type-dependent structures, and the idea is really to track all the constraints we are bringing into the code. So if we have like 10 DSL combined together, we are going to verify that we have 10 interpreters. So if I comment one here, it's going to generate this horrible error. Okay? So I'm not going to read it for you, but this represents the coproduct, and it says, hey, in your list of interpreters, there is one missing for the type, for one type. So you have to check which is missing, and it's terrible. Okay? That's also the problem of Scala-C. The error messages are crazy. Okay? But what is good is that you have, in general, in this kind of libraries, you have 2 or 3 different kinds of type errors. So when you know about them, it's very easy. So you see like 10 lines of errors, and you see immediately you have to search in the right place, and you know what it means, and you know what you have to correct. It's very strict, so it's not, in general, you haven't got very weird error of types, even if it's very long to read. So I'm not going to talk much about this part because I haven't got lots of time. So there is another facility in Freek which is also interesting, a bit experimental, but works quite well. So in general, you have the issues with return types. So we are combining DSL, it's cool, but we have also the return types. So for example, if a guy has no passport, it should be an option of passport. If he has no fingers, it should be an option of fingers, of fingerprint, right? And you have also some errors which are like the camera is broken or the ID service is broken. So you have a XOR. So when you compile it, you have this kind of error. So it says, yes, in your logic, I have no more a picture. It's an option of picture or a XOR of an ID, a picture error and a picture. So the normal case, the normal way you know or not about it in Haskell, for example, is to, or in Scala too, is to use a monad transformer. So you're going to stack your monads, okay? Because the problem of monads is that they don't compose, so you need to provide some helpers to do that, and monad transformer help you to manipulate stacks of monads. There is another way in Freek, so I'm going to skip it a bit, but it's called a Freek onion, because it's exactly like an onion. We are going to stack monads, and we are going to track the types of monads using some path-dependent types, as we can do in shapeless, for example. So it's just an onion like this. So it's I have an option and around a XOR of picture error and around a XOR of ID error. I create this type, which is just a representation of the onion, right? And then I'm going to, so I keep the same program. I create my onion, and then I'm going to lift all the lines to onion. And this function here is going just to take care using some type verification that you can lift your monad, your result into the stack of results, and also that you can, if you have only one part of the stack, it's going to lift it to the complete part, and in general you have all the control you can have, you can obtain with types. And what is interesting also, we provide some helpers to help you manipulate some weird stacks. So sometimes you want to return some list of options or this kind of weird cases, and you have some helpers which are not this one, but other functions to help you to make it better. And at the end here, you have this type. So it's a XOR with a XOR and with an option inside of it. So that's a stack of monads. And what you have to know in this case, it's not like monad transformers. It's reserved to monads which are traversable. But all the monads you manipulate most of the time, like list or option or XOR, either are traversable. So it's quite practical in lots of cases. Yes, so this part is interesting too, but I will skip it just to say that you can combine free programs together. So you can have take one free program, another one, and you can combine them. So I'm calling my first free program, expanding to the combining of the two, creating my second free program and expanding to the combining of the two. So you can take free program and concatenate them. And then you just have to provide one more interpreter and it works. This part is even more bizarre. I wanted to replace, and this works actually, I'm going to replace the logic DSL by another logic, which is represented by a free program. So I'm going to replace the logic by a free of my bizarre logic, right? So here I have the logic, and in the coproduct I have a free here. So now I have a free program which contains a free program. So it's a bit strange. But I can transpile it, providing everything you need. And this free program that contains a free program becomes a free that contains a bizarre logic. So I've flattened the program into one flat free program. So it's a bit weird. I'm not going to spend much time, but it's possible to do it. And it exists in Freek right now. So what is the status of Freek now? So we are in version 0.6.1. For cats, the last version 0.7. We use it in production right now, and it works. You need to use SI 2712 patch, so you need type level Scala. And I advise to use kind projectors, because type Lambda is just crazy. The limits of this model, because there are limits, right? So first of all, we have to translate all our DSL into one single monad. So it's always, it's very, it's not, you can't choose to have different kind of monads at the destination of your execution. So it can be limiting sometimes. So there are other ways of thinking about it. You could transform it into some temporary monad and then into the final monad. But so it's not so cool actually. I hope we will find other ways of manipulating this. The compiling duration. This is the most limiting stuff. So if you take the default implementation of a coproduct as in shapeless, and you have a 10 DSL in your program, the compiling time can become like 30 seconds or 1 minute. So this is a problem, but we have solutions, okay? The wrapping in free, because the interpretation, so we control everything at compile time, but then when we compile into execution into monads, it happens at runtime. So we have to wrap all our structure into free and then to call flat map, and you have lots of overhead on top of your simple code. So this has a cost, but compared to everything that happens in I/O, when you speak to databases or anything else, it's nothing actually, and we don't care about it. The issue you can have if you use some free program which are big or which build some structure which are huge or which are recursive is a garbage collection, because you are building lots of small structures which are very, very short-living. And then the JVM can hit the garbage collection limits, and then your solution in production can have issues. We have never had this one, but I know other people, like Tim Perret, he was speaking at Scala World 1 month ago. That's something they care about. So globally, I say, if you want to do high performance in real time, don't use free monads for now, okay? It's a good idea, but not for that. But globally, you don't need that most of the time. It's not really a problem. So there are solutions to help us. So for runtime, so all we can do is to optimize the free representation. So there are lots of papers about it. We have already in CATS the right association which helps a lot. And there are papers about having a structure, because so a free monad is a bit like a sequence. And it's a bit like appending, okay? When you append, if your sequence is very long, it's very long to append. So the idea is to have something in O of 1 appending, okay? And there are some theories about it with reflection without remorse on or freer monads, and it's applied in a project called Scala F, and it works. Ideally, we would like to eliminate the free structures at compile time. We would like to compile at compile time, actually. So for free applicative, so I'm not going to spend much time about it. Free applicative is an applicative which is given to you for free, and this one is known completely at compile time, so you can compile it at compile time. Free monad, it's much more complicated, because the A gives M of B is something that will happen at runtime, and you don't know what will be the result. So it's quite hard to do this part, but maybe with some, I don't know, evolutions of language and maybe Scala meta or whatever, we might find some ideas about it. For the compiling, so I said it's an issue, but we have solutions. So first of all, why is it an issue? It's because the compiler, so Miles Sabin would explain it far better than me, but globally, it's accumulating implicits. And the problem is that in our case, we have a sequence of structure which are induced all after one another. So you have one implicit which depend on one implicit which depend on one implicit. And every time it's going to accumulate implicits. And so the more your sequence is deep, the deepest it is, the longer it will spend. And it's kind of exponential. But so we have a solution right now in Freek, which is quite cool. We have this for the representation of Coproduct, so it's a sequence. And we have transformed this in a tree, like a B tree. So here you have 4 in-depth, here you have 2. And this so it's just an optimization of the structure for compile time. So it's a trick, but we have reduced completely the time of compiling by 2 or 3. And in big cases, it's even more, it's 4 or 5. So it's already quite cool, so you can compile your free program even with 10 elements, and it's quite acceptable. And it's not, if you have a big cake pattern with 10 elements, it's also very long. The real hope is about this, okay? Because I hope this guy will succeed. Miles is working on optimizing implicit induction, and maybe we'll have something which is quite better. And if it works, what I was talking about will not exist anymore. The only burden you will have is garbage collection and wrapping of your structure around free. What is the future of this? So we have different talks speaking about extension, speaking about DSL, about what will language be in the future, about representation. And it looks like Free is now efficient. It's a step further compared to what we had before. So dependency injection at runtime or all this kind of stuff shouldn't exist anymore, okay? It's something which is just a solution for Java. But for Scala, if somebody is using dependency injection at runtime, it's just a failure. So we have, this is very good for now, but it looks like there is something further. So I don't know exactly what it is. We are all like trying different solutions, and we'll see what happens. And there are also other solutions already existing. So you have monad transformer, which are quite good already. You have also finally tagless, object algebra. You have other representation of Free with van der Rohe. And you have also some other model of computation which are oriented about effects only. So you have the famous Freer monad, which is implemented in Scala F in extensible effects. You have Idris F, which apparently is kind of deprecated. and maybe there are other solutions, I don't know. So what will we do? So maybe we will have better support of DSL and combining DSL in the host language. In the host language. Maybe with some macro or some extensions. So maybe we can ask Eric about it. Or better host languages directly, and better runtime also, because we are talking about applying Lambda calculus directly at the runtime level. Type-dependent languages are very interesting also, even if they are quite complicated to manipulate for everyday life. Maybe we will reach a level when they become very, very good for our everyday life. So we'll see. I don't know. There are lots of studies. What is good is that you can use this kind of tool right now in production, in Scala, and I feel like I'm quite happy about it, because I was surprised that it would be so simple and so easy to use for somebody knowing nothing about free monads and coproducts. So I wanted to finish on this, because, and this is not a lie, right? And finally, thank you.